All right, this is for dynamics, chapter 16 homework. Um, so the first problem, it's a bar with wheels. Essentially, it's moving to the right because of the force P. Only moving in the x direction because the wheels are essentially keeping it in place. And we're looking for the acceleration of the rod and the reactions at A and B. So pretty much you can write this out by just summing the forces. We know that ultimately it's going to be not moving in the y direction, so the two reaction forces are ultimately going to equal the weight, as well as like any rotational motion from the moments. And in the x direction, it's going to equal, the force that's ultimately affecting it, which is going to be the mass times the acceleration. So, what you do is we know the total force in the x direction is going to equal the p force, which is 8. And we know the mass is 2.5, so pretty easy to solve for the acceleration that way. For the reaction forces, we actually have to use the moments around B, which is this top corner. So we know that all the external moments, if you sum them up, it's gonna equal the moment affecting the rigid body itself. So that is ultimately going to equal mass times acceleration times 2r over pi. So you can basically just plug these numbers in. So we're going to have the reaction force at A, which is the radius away from B. Yeah, that's one radius right there, which is 0.3. And then we have the weight. So this is the mass times acceleration times the perpendicular distance, which is going to be this little gap right there. So it's 0.191 minus, or 0.3 minus 0.191. And this is found you can just look it up through the centroids of an arc. It's this 2r over pi that we were talking about before. So that's how you find that value. And then that's going to equal the same thing, that distance times the mass, and we solve for the acceleration, so we have that as well. So you can solve for RA pretty easily, and then from there, we're only looking for forces in the y direction, and we know it's not moving in the y, so it's pretty easy to solve for the reaction force at B. Here I just labeled it wrong. It's actually moving up because I ended up with a negative answer. So that's it for question number 1. For question number 2, we have the triangle connected to some pins right here that are moving down. And it gives us like the mass and everything. So pretty much how you go about solving this one is you want to set this up. Sorry, paper's getting all messed up. So you want to set this up using the normal and tangential coordinate system instead of xy, because we know that it's moving in a circular path because of how the slots are on the pins. So we know it's going to be rotating in that direction ultimately. It's going to have a tangential acceleration. It's also going to have, the acceleration pulling it back towards the center of rotation. So we can see here that it's going to have a total acceleration combination of these two vectors, one in the tangential, one in the normal direction. So for the tangential direction, we just have this vector, the weight vector, split into the tangential components. So that's the mass times gravity is going to, the tangential component of that, which is the cosine 30, because we just want this side here in the tangential direction, is going to equal the mass times the acceleration in the tangential. So the mass will actually just cancel out, and you can solve for the tangential acceleration pretty easily. So For the normal, you can actually just use the v squared over r. So we know the r is 6 inches, and we know that the velocity is 30. I believe that was given to us. And so we ultimately know, so the 30 is just the yeah, so the 30 is the velocity. So ultimately we know the normal component and we have the tangential component, so we can calculate the overall acceleration, which, like I said, it's going to be in between these two vectors. And we can solve for the total acceleration and also the angle in between them. So this is in between the tangential axis, because that's what coordinate system we use. So I actually just switched the tangential into the x and y coordinate. So we know that it was 60 degrees. If you look back at this triangle, here it was 60 degrees from being perpendicular. So that's essentially how far off from being x, y we are. So if you just add 60 degrees to the arctan of the y over x, you can actually just solve for the total angle from the x-axis that way. And then from there, we can actually just sum up the moments. So we know that if you sum up all the moments at any point, it's going to equal the total moment affecting it, like the net moment. That's actually affecting the object. And we know that is going to be the so I'm losing my train of thought here. So it's going to be these two forces. I didn't label them on this triangle, but I did on this one. So it's going to be the force at B from this one and the force at A from this one. But since we're summing the moments around A, we only need to use the force B times the distance, which is 9, and the component, since we're switching it back to x and y. So we only need the x coordinate for this one, because and then this part is the moment from the weight. So this is the weight, the mass times gravity times the distance, which is 6 inches there, as you can see. And then that's going to equal the mass times acceleration. So this is the mass this is the weight divided by gravity to give us the mass times the acceleration. And that's ultimately going to be multiplied by these two components, because this is creating a moment around A in two different directions, because it's pulling down and it's also pulling this way, so it's pulling in both the x and the y. So this is just both of the components. You can just factor out the acceleration and the mass, and you can calculate B that way. And then from there, you can just sum all the forces in the x direction and solve for A pretty easily that way. So that's pretty much how you do it. Now that you solve for B, pretty easy to solve from A from there. So for 3, this one was the 2 discs. Yeah, so this was the 2 discs that they're pushed together. This one has like an initial angular velocity, and this one starts at 0. They're pushed together, and essentially we're trying to find when. And there's a coefficient of static friction in between them as well. So basically what I did is I just solved for, I just wrote out the diagram here because it tells us that they're pushed together with a force of 20 newtons. So we have the force of 20 newtons. We know the coefficient of static friction is 0.15, so you can actually solve for the force pushing up from the, other disk running into it, you can say. So I just converted the rotations, the RPM to angular velocity, and then I summed the moments around the center because we know that it's not like rolling. It's just rotating around a fixed axis. So we can just do it around the center in this case, and we know that's going to be the mass moment of inertia times the acceleration. We know the mass moment of inertia for a circle is 1/2 mr squared. So all these are given to us. We can solve for that pretty easily. As far as the moments, the only one acting on it is going to be the force from the friction, because this 20 Newton force is going right through the center. So that's not going to apply a moment to A. And we know that it's going to equal the mass moment of inertia times the angular velocity. We already solved for the mass moment of inertia, so we can just solve for the angular velocity that way. And then you can just do the same thing for the other one. So this is for the smaller circle. And we are just going to solve for the moment using the same concept. So we have the same force because it's Newton's laws, equal and opposite. So this is also going to be the force on B. Radius is a little smaller, so the distance from the center is a little smaller. And that is going to equal the new I, which is the new measurements, same equation, times the angular velocity of B, and you can solve for the angular velocity of B that way. So for this one, we know when it stops moving, there's going to be no more slip. So we know that the distance covered by one circle or disk is going to equal the other one, because it's however far one moves, the other one's going to move. So the distance at the edge is the angular velocity times the radius of the circle. So we know that the radius times the angular velocity is going to be equal to the radius times the angular velocity of B, because this ultimately equals distance. This is where it gets a little tricky. So for the angular velocity, we know that it's initially 37.7, and it's deaccelerating, it's slowing down by 12.5 rads a second squared. So we can actually use kinematic equations here, and I'm going to plug in, because this ultimately, if we have the time, will give us the total angular velocity when they equal each other. We just don't know how long it's going to take. And then that's the radius. And then this one, we only have the angular velocity, the angular acceleration. We don't have an angular velocity. It starts at 0. So we know the final angular velocity is going to be the angular acceleration times time. So you can actually just distribute this and solve for t, and that gives you a time. And then from there, you can just use regular kinematic equations to solve for the final angular velocity for both of them. So this is just angular, I explained that in the previous section. So, all right, and then for 4, this is the drums. So how I went around solving this one is we're ultimately looking for the radius of gyration. And we know that there's a couple ways to solve it. We know that the radius of gyration equals mk squared. It also equals the mass moment of inertia over mass. So ultimately, I just solved for the angular acceleration, just so I don't have too many unknowns, and that's pretty easy because we can solve for the regular acceleration by just using the net force in the y direction, and then we can use that acceleration to solve for the angular velocity because we have the radius of the circle itself, which is 0.2, because it's ultimately going to be rotating somewhere in this, section because it's getting pulled up right there. So yeah, we can solve for the angular acceleration, and then we can just solve for the moments about g, the center. And from there, we know that's going to equal the mass moment of inertia times the angular acceleration, which we already solved for. So plugging everything in, we have the two rope forces times their distance from the center, times I times our angular acceleration. So we can solve for I that way, and then using this equation, we can solve for k pretty easily, which is just I over m square root. So there we go. That was number 4. Pretty simple. Okay, and then 5. So 5 is the bar, and it's rotating not about its center. Initially, I thought this would be a parallel axis theorem problem because, it's easy to calculate about the center of gravity. And then you can just use parallel axis theorem to calculate. But I realized we actually don't have like that mass. Maybe we could use like a ratio to find how much mass is actually away from, that section or whatever. But there is another way to solve it. So you can solve it by solving for the moments about c. And we know that the total moments affecting it are going to be the force times the distance, so whatever force is applied to it, which in this case is the 75 newtons, plus the mass moment of inertia times angular acceleration. So we can solve for I. This is just for the rod in general, 1 over 12 L squared times m, and that gives you the mass moment of inertia. So we can just solve for the moments here. So we have 75 newtons, and then this distance is going to be half of 0.9 plus 0.225, and then we have the effective moments. So we have the and this force right here, I forgot to mention this, can be written as the mass times acceleration. And the acceleration can be written as angular acceleration times radius. So this actually just gives you 4 times the angular acceleration, times r squared. And then that's going to be in addition to the I, angular velocity squared. And from there, you can just solve for the angular velocity pretty quick. And then from there, we can just sum the forces in the x direction. So we know that the forces in the x are ultimately going to equal the mass times acceleration of the bar itself. So we don't have the actual acceleration, but we have the angular acceleration, and that the regular acceleration equals angular acceleration times radius. So we can plug that in there, plug in the mass, and then we have these two forces. So there's a reaction force at C, and then we have the force P, which is 75 newtons. So we know that that's going to be, you can just solve for that pretty easily, and that's going to be in the positive x direction. And then the forces in the y, it's not moving in the y, so we know that's ultimately going to be 0. So Cy is just going to be the reaction force to the weight, mass times gravity. So you can solve for Cy that way. Pretty simple. Alright, so for 7, this one, or I feel like I skipped one. Did I skip 6? Yeah, I did skip 6. So this is the symbolic one. Ultimately, we're just looking for the acceleration just written as a function of, all the variables. So you can do that by just, so I wrote it this way. So this is flat because I want to use the xy coordinate when, everything's flat, and then I can just convert the weight vector into x and y components, because ultimately I'm going to take the moment here about c, and the y component goes through c, so there's going to be no moment there. It's only going to be the x value, because that's really the only thing pulling it down, causing it to rotate when you think about it. So the moments about c, we have mass times gravity times the sine of br, because we only want this x. The component in the x direction is the sine of beta, times the radius of the circle, because that's how far it is from C. And then that's going to equal the effective moments, which is force times distance. In this case, it's mass times acceleration times distance, plus mass moment of inertia times angular acceleration. Just like the previous problem, we know acceleration can be AR, so that's going to give us r squared. And then this is the I can be written as mass times radius of gyration squared times the angular acceleration. So yeah, just write it out this way. You just solve for angular velocity pretty easily. Just combine these two, factor out the angular velocity, and then divide it by whatever's left, which is r squared, k squared. And then same thing again. So we know acceleration is going to equal angular acceleration times radius. So we're just going to throw in another r there to give us the total acceleration. So pretty simple. For 7, this one is another drum one. We're looking for whether or not the disk slides, the angular acceleration of the disk, and the acceleration of g. So basically how fast it's spinning and how fast g is moving upwards. So I have excuse me, I have my diagram here and all the variables that are given to us. Weight in pounds, so we're going to have to ultimately divide by gravity to get the mass. Our two coefficients of friction, kinetic is always a little less, and then our radius of gyration. Okay, so I just started by solving for the mass moment of inertia by using the radius of gyration. I converted this to feet, which is why that's divided by 12. And that's going to give us our mass moment of inertia. And then the acceleration, same thing as before, r alpha. And I, again, converted that to inches. And then I actually just took the moments about c. So ultimately, we know the moments about c are going to, if you sum up all the moments, it's going to equal the net moments that are affecting the disk itself, which is going to be same thing as before. It's mass times r squared times angular acceleration. And then you're going to add the mass moment of inertia times angular acceleration to that. So we have the force. So we know the weight goes through c, so there's going to be no moment. So the only moment at 4c is going to be this 5-pound force pulling up, and the distance between it, which is 4 inches, again, converted that to feet. And then here we have the mass, which is weight divided by gravity, times our distance, that's the radius in converted to feet, times the angular velocity, and then Ri times our angular velocity. So we can just put these together and solve for the angular velocity that way. And then we know that the forces in the y direction are ultimately going to be 0, because when this gets pulled up, it's ultimately going to pull, it's going to wind it up and move it in either the negative x or positive x direction. So we know this is ultimately going to be 0, so we can actually just solve for the normal force pretty easily. And we know that's just going to be the opposite of the weight, which is going to be 5 newtons. And we can apply the coefficient of static friction to that. So we know that it takes 1.25 pounds to move the thing to get past the coefficient of static friction. So now we can actually just solve for the force itself. So we know the only thing acting in the x direction is going to be the force from the friction. That's the only thing that's ultimately going to be moving it in the x direction, since the force is in the y direction. It's only from the moment. That's the only thing that's causing it to move. So we know that is going to equal the mass times angular velocity times r, mass times acceleration. So we can just plug in all the numbers and we get a force. And this force is bigger than our force we calculated with the coefficient of static friction. So we know it's gonna be moving ultimately. And the last question here. Sorry, this is kind of a long video, a lot to explain. So this one was the two circles, and there's a bar in between them. I think I may have actually been a mistake on this one, if you're still watching the video. So we know that there's going to be no slip. So because there's no slip, however fast A is accelerating, it's going to be moving. It's going to be moving the bar. It's all connected and rigid, so that means B is going to be moving at the exact same speed. And if B is moving at the exact same speed because they have the same radius, the angular acceleration is going to be the same between them. So there's only going to be one angular acceleration, so I just didn't label them. And then I went ahead and just took the moments about E on the A disk first. So we have the total moment, which is given to us, which is nice. And then we have the force at C from the bar times the distance, which is the radius minus that 0.04. Yeah. Okay, I just want to make sure I did I forgot to include a 0 there, so I just wanted to make sure I did it correctly in my calculation. And then that's going to equal the, effective moment, which is I alpha squared plus the mr squared alpha, mass times acceleration. So you can just plug in all these numbers, and we're going to get an equation with both two variables, and it's going to have c and it's going to have alpha. So it's going to have the force pulling it that way, and it's going to have the ultimate angular acceleration of the disk. And then I did the same exact thing for D. Just solve the moment about the point in contact where we know it's not moving, and you get another equation. And this one, we know D equals some coefficient times alpha. And then I just do it for the bar itself. We know this is ultimately going to equal the net force, which is going to equal the net mass times acceleration, however fast the whole thing's moving. And that's going to equal D minus C times mass times acceleration, which is angular acceleration times radius. So we know D and C. We have D and we have C, and these are both in terms of the angular acceleration. So we can solve this pretty easily. So the mistake is actually right here. So I was looking in the solutions because I couldn't get the right solution, and I'm pretty sure this is supposed to be the mass of the bar, which is 2.5 kilograms. In the solutions, it uses the mass of the disk, which is 2, which doesn't make sense since, we're talking about the bar. So ultimately, you can solve for the acceleration and then plug the acceleration back into this equation to solve for D, and that will give you the force in newtons. Thanks.